Hello everyone, welcome back to our lecture content. Today I will talk about system stability, so stability of dynamic systems. So we will take a look at what is stability, how we can define it for dynamic systems, and then later on we will talk about a number of techniques that we can use in order to analyze stability and design systems that will exhibit the desired stability properties. Okay, so let's put our title here, which will be stability analysis and design. Okay, remember the same concept applies. The fact that we can use the same tools in order to analyze a given system, or if we parameterize the system based on certain, for example, controller parameters, we can use the same tools in order to specify what we want in terms of stability, and we can find the required parameters for a controller to give us those specific properties. Okay? So let's consider a system which is given an input, okay? And we assume that our system is composed of a transfer function, which basically has a rational function, is composed of a rational function of s with a numerator polynomial p of s and a denominator polynomial q of s. And it actually generates an output y of s. So we have just specified in the frequency domain, we know that the transfer function concept is a frequency domain concept, okay? So what we know is that given this, the output of this system is actually the product of this transfer function, which characterizes the system, times the Laplace transform of the input. Okay, so if we consider the rational function that we defined, essentially the numerator will be composed of p of s, which is the numerator of the transfer function, times u of s over q of s. Obviously, here we don't specify u of s, but obviously u of s may also have a numerator and a denominator. Okay, for example, a unit step function in the Laplace domain is 1 over s, and that means it's gonna give us something in the denominator. Okay. So what we know also is that the output of this system is determined determined by the inverse Laplace transform of y of s. Okay, so if we wanted to determine y of t, we will have to take the inverse Laplace transform of y of s. Okay. And if we do that, and we have done this for first and second order systems, we have seen that y of t will basically have, depending on what we have in this product, p of s, u of s over q of s, y of t will have exponential components, exponential and or sinusoidal components, okay? Sinusoidal components. Sorry, let me erase this. Oops. Inverse Laplace transform of y of s. Y of t will have exponential and sinusoidal components. Sorry about that. It's kind of requires getting used to using this pen on the screen. components depending on actually the roots of this Q of S is equal to 0. Okay, this denominator over here. Okay, and this is known as, let's use some color here. This is the characteristic polynomial, and this whole thing is known as the characteristic equation, right? Characteristic equation. Okay, so for example, if this polynomial, this equation has only real roots, okay, we will have only exponential components in y of t. If this equation has complex conjugate set of poles, then we will have exponentials multiplying sinusoidal components. So we will have so-called damped sinusoids, okay? Now, the roots of Q of S equals 0 are also known. We know that these are known as the poles of the system. Okay? All right. So now conceptually, we have previously discussed that these poles, the roots of the characteristic equation, have basically very important, or determine the very important properties of the system, because the behavior really depends on those poles, okay, whether they are real or complex conjugates and so on. Okay, so conceptually we can again try to define the stability. Okay, conceptually a system is stable means system is stable means that for a bounded input, it does not blow up. Okay, very informal kind of putting it. Okay, blow up. So I'm gonna put it in within quotes. Okay. So stability is if we supply the system with a bounded input, for example, a unit step, which is a bounded input, but unit ramp is not a bounded input. Okay. And what we mean by blowing up is that something inside the system does not go to infinity. Okay. So if we kind of divide this into two, okay, so we may mean that the output does not blow up. Okay, become unbounded. Or in fact the inside does not blow up. Okay, so why do we make such a distinction? Because we will discuss in a minute cases where in fact the output of the system may appear bounded, but the inside of the system may become unbounded. Okay, now this one would basically or usually means what we call the input-output stability. Or bounded inputs and bounded output stability. So this is known as the so-called Bibo stability. So if we have a bounded input, we have a bounded output. Obviously, if you don't have a bounded input like a ramp, a system may still be stable, but the output, you don't expect the output to be bounded if the input is not bounded. Okay? And if you're talking about what the inside of the system is doing, is usually what you mean is state stability. Okay? State stability. So what you mean is if you have a bounded input or a bounded state, all the states, okay, all states remain bounded, okay? So we will later on, when we will be studying state space, we will spend some more time on what stability means for state space systems or state space description of the systems, okay? So I'm having some difficulty with the slide bar, okay? So so if we have a bounded input, or let's say if we look at y of s, okay? Consider y of s, okay? When do we have bounded behavior? Okay, so I got a phone call from the department, so I had to go and come back. So this is all new. And also I feel very slow, so but you guys have the ability to fast forward, and you know, my son is watching some YouTube training videos with 1.25 speed, so maybe you can accelerate also the speed, so I will have a different voice for you. All right, so when do we have bounded behavior for y of t? Okay. And the answer is that if we have essentially all roots of q of s equals 0 having negative real parts. Okay, so that means that if we take a look at poles and zeros, okay, and in fact the poles of the system, the roots of q of s is equal to 0, if these are on the left half plane, okay, so this part results in unbounded behavior, and this part results in bounded or stable behavior, okay? Bounded or stable behavior. Okay, so why is that the case? Well, we know that because these negative real parts essentially results in exponential functions with a negative exponent. So that means as time goes by, these exponentials decay down to 0. Therefore, the contributions become less and less, and therefore the output converges to a value in the limit. Okay. Now, is there a catch, or is there something we need to be aware of? Okay. Because remember that y of s, actually, when we are computing y of s, we have the transfer function t of s, but we also multiplied with the Laplace transform of the input. So what can happen is that, and we are looking at the denominator of t of s, which is q of s. So what might happen is that when you multiply it with u of s, you might actually cancel out some of the poles of t of s. Okay, so important or interesting question is what happens if there is what we call a pole zero cancellation. Pole zero cancellation. In fact, this doesn't mean that T of S has a zero that cancels a pole, which might also be the case, but U of S introduces certain components that actually cancel out some of the poles of T of S. Okay? So in that case, the output may appear to be bounded. The output may appear to be bounded, but some of the states, the internal variables, or some of the internal variables may actually become unbounded. Okay, but the system may become unbounded from the inside. Okay, so you can see that sometimes the system may appear to be bounded input, bounded output stable, but in reality it may not be internally stable. Not some of its internal variables may be unbounded. Okay, why? Because the output does not show some of the internal behavior because of a pole zero cancellation. Okay. So as I said, we have these two concepts, the bounded input, bounded output stability on one side, and also state stability, also known as asymptotic stability or state stability, which is essentially a stronger condition. Okay, so what we do then is not to consider the input or what the input does to affect the output, but we look directly to the denominator of the transfer function, and we consider that to be a characteristic of stability. Okay, so let's put here we consider all roots of Q of S equals 0, the poles of the system, and we study them as a characteristic of the stability behavior of the system. Okay, of the system, to analyze the stability of the system. Right. So what are our statements on those poles of the system? Okay, for majority of systems, we have the following results in terms of stability. Okay, the first one is if all roots of the characteristic equation right, poles have negative real parts, then we say that the system is stable. Okay. The second statement, if there is a root with a positive real part, even a single root with a positive real part makes the system. So if there is a root with a positive real part, or a repeated root on the j omega axis, repeated root means that you basically have, right, two poles at the same location on the j omega axis. So this condition requires at least 4 poles on the j omega axis. Then the system is unstable. Okay. And finally, if one is satisfied except for one or more non-repeated poles on the j omega axis, then we have the system as critically stable. You see, for the case of, for example, our second order systems where we analyze this behavior, right? This critical stability means that you have 2 poles on the j omega axis, and you guys know what that means, right? You basically have non-decaying oscillations. So you have permanent oscillations. They do not diverge, so you have actually bounded behavior. But unfortunately, the output does not decay or it does not converge to a single final value. Okay, so that's why we call it critically stable. Okay, sometimes it's also known as limitedly stable. Okay. Now, obviously, we know how to analyze first order systems and we know how to analyze second order systems. But if you have a system with a large number of poles, okay, now what we are saying is that we can analyze its stability by looking at the closed loop poles, the roots of the characteristic equation. But since if you have a higher order system, basically, you cannot talk about the exact behavior of the output or the exact behavior of the states without resorting to some kind of computer tools. Okay, obviously you can use, for example, MATLAB's root finding function called roots in order to find all the poles of the system. Therefore, you can talk about its stability. But you need to find out the response, for example, a step response of the system by using, again, a MATLAB tool like the step function in order to find out about what's going to be the output. Okay. So, the tools that we will learn in the coming lecture will give us a hand and, a pen and paper type of tools to talk about stability, but they will not give us tools to find out about the exact performance parameters of the system. Okay. So let me explore some of the tools that we have in order to analyze stability. Analyze stability. Okay, some of the tools that we will learn in the coming lectures. So if we take a look at those, the first one is basically that you can determine the exact roots of Q of S equals 0. You can do this obviously either by using direct numerical solution. For example, in MATLAB, you have the roots command, function. Alternatively, we can this does not specifically mean that we determine the exact roots, but we can use the root locus method. Locus means kind of trajectory. Okay, so this method actually allows us to sketch how the roots will move as we vary one of the parameters. Okay, so trajectory, an analysis of the trajectory of the roots of Q of S equals 0 as we change one parameter. In the system. Okay. Another way we can attack this problem is, can we determine the region of some system parameters for stable system. Okay. So one very nice method to be able to do that without solving for all the roots is called the Routh-Horwitz criteria. Routh-Horwitz criterion. Okay. Actually, what this criteria does is that for any higher order polynomial Q of S, it will tell us how many of the roots are actually having their real parts in the unstable region. Okay, so tells us how many roots are unstable. And we will see in the future, in the close future, is that in fact we can extract more information than that. For example, we can extract information about symmetric roots and stuff like that. It's a polynomial analysis method that is very powerful actually. It doesn't require the solution of all the roots, but it still gives us very good information about the behavior of the roots. Okay, there is also here the Nyquist stability criteria that we will study, and this gives information, gives info about the closed loop poles, that means roots of Q of S equals 0, using, without determining the closed loop transfer function, using only the open loop transfer function. Open loop transfer function. Okay. And finally, what we have as a tool is direct numerical simulation, which is direct numerical simulation. You can call this trial and error because what this means is that you give certain values to some system parameters. You find y of t, for specific u of t's and system parameters. The bad thing about this is that you have to have many trials by giving different values to different parameters, trying different inputs and so on. So you cannot get a generic result about a system, but you have experience or you have results for specific instances of the system and specific instances of the input. Okay, so that concludes our general discussion about the definition of stability, bounded input, bounded output stability, internal or state stability or asymptotic stability, and how we justify using only the roots of the characteristic equation or the poles of the system in order to study a system stability when its transfer function is given. Okay. Later on, when we will study state space systems, we will also discuss how that translates into a stability definition in the state space. Okay. So I'm going to continue in the next video using the Raut-Horwitz criterion. Okay. One of the tools. Horwitz, sorry about that. It's a Horwitz criterion. Okay. So see you in the next video.